Hello everyone. My name is Ruitao Feng and from Singapore Management University. And today I will present our work on the malicious behavior detection for IoT malware with multi-level classification. And this work was collaborated with researchers from SMU Tianjin University and Nanyang Technological University. So in this presentation, I will first introduce some background knowledge and illustrate the motivation approach evaluation in order, and then conclude the presentation. So recently, the rapid growth of IoT devices has brought convenience, but also enlarged the impact of the inadequate security mechanisms for some security scenarios. So developing certain security technologies for those IoT devices could become urgently needed to fight against potential adversaries, especially the malicious software providers. And by reviewing the state-of-the-art approaches and tools for the IoT-specific malware detection and analysis, the existing can be summarized into two main categories: the static analysis based binary and family classification, and the sandbox based on the dynamic analysis. But the problem is both of them have to have their own specific problems. For example, the static analysis based classification may overlook some malicious activities in the decision-making process and always needs extensive domain expertise and efforts in the post-detection analysis. And the dynamic-based analysis offers more detailed insight which could guide further analysis, but the problem is this kind of approach always needs lots more computational resources, which the IoT devices will never offer. So based on such observation, a research question came to our mind. Can we identify the malicious behavior promptly? And we firstly conducted a large-scale empirical study on a dataset of more than 5,000 IoT malware collected according to the three main data selection criteria from different sources. And the first selection criterion is based on the macro ratio of all data, which we want to ensure the distribution of our study samples is highly similar to the reality. And the second is to prioritize the new malware families. And the third is to select those representative samples from those highly similar clusters. In the study, this first step was the in-depth analysis of the report collected from the antivirus engine, from the virus total, and the sandboxes widely adopted by the industries, such as MITRE, to obtain the potential malicious behaviors. And further, by analyzing the report, we can produce a rough malware attack chains with the help of the TTP from MITRE attack template. And leveraging reverse engineering to Ghidra, we first statically analyzed the program level implementation of each malware and summarized a detailed taxonomy of malicious behaviors consist of the stage and the behavior exhibition, attack method, and the implementation of that attack chain. And this malicious behavior summarized from the real-world samples serve as the ground truth in our study and also the experiment, and plays a vital role in constructing the test dataset. And with such knowledge, we observed some interesting phenomenon. So we observed the node in the function call graph which generated from the IoT-specific malware are always farther away from the entry node of the malware. But the problem is these type of nodes contributed less and limited value in understanding the semantics of those malicious behavior and also contribute fill in producing the malware attack chain. So we doubt whether they could bring negative impact to the graph learning method in capturing the semantics. So subsequently, we introduced a graph masking method to eliminate this type of node from the function call graph. And this graph masking method mainly consists of three steps. The first step is the central node obtaining by computing the graph centrality, and the mask radius calculation by computing the path distance between the central node and others. And finally, we can then determine the mask about which node we should remove from the FCG, which node we should keep in the FCG. And based on the graph masking method, we further proposed the overall approach, MaGraMal, leveraging multi-label classification to identify the malicious behavior from malware, the IoT malware. And this approach has 4 steps. The first is the original function call graph representation, and second is mask graph construction. The third is the feature vector extraction, and finally the model construction. And along with the graph masking method, we would like to highlight another subside novelty, which is the adoption of graph structure feature. And the evaluation of this work was organized into 3 perspectives: the effectiveness of the tool, the soundness of the crucial designs, and the real-time performance. The effective evaluation was conducted on 224 multi-label classification algorithm combinations, and the results demonstrate our work exhibited good accuracy but not perfect. For example, about 80% on the correctness of labels and 30% on the correctness of samples. The correctness of labels here, namely label accuracy average, represents the ratio of the correctly predicted labels among all, and the correctness of samples, namely the sample accuracy, represents the ratio of samples whose label were entirely predicted or entirely correctly predicted. And to answer the research question, the second research question, we evaluated the result of different balance parameter alpha. And in the figures on the left hand, we can find 0.7 is the matching number for our data set. And that means by applying the graph masking method, the effectiveness of this model has been enhanced a bit. And secondly, we conduct an ablation study to demonstrate the superiority of the innovation method, which is the graph masking and the adoption of the structural features. And in this experiment, we leveraged 5 different types of metrics, and for most multi-label classification method, our proposed design, our designed method has achieved a better result comparing to the result without them. And regarding the performance, we compared the runtime performance of the Lisa sandbox, which is a popular tool in the industry, and the results show that our MaGraMal costs much fewer resources. However, also are able to point out the target lurking behaviors. And to conclude the presentation, firstly, we proposed a multi-label classification approach for detecting the lurking behaviors. And besides, we also released the annotated dataset to the public, which cost a lot of effort. And certainly this approach also have some limits. For example, we find there is a trade-off between keeping the key information and removing the redundancies in the within the mask. So we thought about whether we can have a more adaptive masking method in the future. And besides the trade-off, we also find the current approach has could be easily bypassed by adversarial samples. So we believe an adaptive approach could help us solve this problem. And the third is the limited training data, because in our study we placed on a smaller size data than the reality, so it would be a great idea if we could find any lightweighted but more powerful program analysis and semantic validation method to enhance this point. So any questions?
Okay. The next speaker. Any questions? So I have a question about the data sets you use. Do you have all the malicious behavior precisely described, or they still have some undescribable behavior, but still malicious?
The methodology used to build the ground truth is we start from the malware report, and we use as the guideline. But after obtaining and analyzing the report, we dig into the implementation of the malware by reverse engineering the malware and analyzing the code. So basically, in short, our ground truth was built upon the malware, the sample analysis.
So this means that you still have false negative, right? Because not everything is correctly reported for the negative side. There could be some unfound malware functions.
Yeah.
Okay.
Because it is quite a huge effort in analyzing those malware. So with our effort, we can only handle like as much as 5,000.
But you mentioned that you did that manually, so you did it 5,000 analysis manually or with some automation?
Basically, it was conducted manually. But we use the report as a guidance. That is why we start from the like using the static analysis to build the FCG and also use the regenerated report as a reference, as a coarse-grained malicious behavior explanation.
But this means that this method is not possible to be extended with larger data, right? So if you have to do this manually.
Yeah, we are thinking about this. We are thinking about any potential extension from this point, because if we can solve this problem, we can automate the whole process and save a lot of human effort, and maybe try some novel machine learning or deep learning method on a huge data set.
Okay, any further questions or suggestions? If not, then next speaker again.